Friends, we would like to learn about moment of inertia. So the moment of inertia is important topic. So let's learn the basic concepts of moment of inertia of a section. So here section refers to an area of cross section. The moment of inertia of a section is defined as the resistance offered by a section or the area of the section during its rotation about an axis. So the moment of inertia of a section is the resistance offered by the section or the area during its rotation about an axis. So if you look at this particular section, so this section is of rectangular shape and it is rotating about this axis, which I have shown by x-axis. So if you see here, this plane is going to rotate due to application of moment of force. We can say it is going to rotate like this, friends. So here you can easily identify the plane is rotating about this particular axis of rotation like this. So in this particular case, when the plane is rotating about this particular axis, what are the factors on which the resistance offered by this particular plane during its rotation changes or depends? Okay, so we need to understand that the rotation of this particular plane will be affected by two major parameters. The first parameter is area of plane. So the resistance to the rotation of this particular plane will depend on the area of the plane. So larger plane will have larger resistance to the rotation. So that is because of inertia of that particular area. Okay. So we know that if you increase the area of this particular plane, definitely the mass is going to increase of the member, and hence we can say the area of the plane would cause resistance to the rotation. So this is the first factor which causes the resistance to the rotation. Now the second factor is the distance of area. So if this area is very close to the axis of rotation, you will see the plane can easily rotate. But if I move this particular area away from the axis of rotation, you will find the more resistance will be offered by the plane to the rotation, something like this. So here you can see we are moving the same area away from the axis of rotation. So in that case, the resistance to the rotation will increase. So here the area has gone shifted from the axis of rotation. So this distance, which is the distance from the CG of this particular area, centroid of this particular area to the axis of rotation. So as the area is moving away from the axis of rotation, the y is going to increase. So therefore y is going to affect the rotation of the section or the area. So that is why we have written here the distance of area from the axis of rotation also causes resistance to the rotation. So these are two factors which are causing resistance to the rotation of the plane about the given axis of rotation. We have seen that the moment of inertia of a section is the resistance to the rotation of a given section, right? And in that case we can write down that moment of inertia I. So moment of inertia we represent by this letter I. It depends on the first factor is area of the section, and the second factor is the distance of the section from the axis of rotation. So I can just write down that it depends on A into Y, or I is proportional to A into Y. But if you look at this particular diagram, if I see this upper area, so for this Y will be positive. To see this area which is below, so for this Y is going to be negative. So here if I write down inertia equals A into Y, so for the upper portion of this area, the inertia is going to be A into Y, and for the below portion of this area, it is going to be A minus Y, A into minus Y. So if I combine both of these together, in order to get combined moment of inertia, this will be cancelled out, okay, because one is positive and one is negative. But in actual practice, the below area as well as above area both are causing resistance to the rotation. So to minimize or to reduce this particular effect, that is called as nullification effect, we cannot take the sign of y. So we have to take absolute value of y, and therefore for distance of area from the axis of rotation, we don't take y directly. Instead of that, we take y square. So whenever we'll take y square, friends, that negation or the negative effect of the area which is below the axis of rotation will be ruled out. So we will be getting only A into y square for both of the cases, right? So that is why moment of inertia is simplified in this particular way. So the moment of inertia is taken as the product of area and square of distance of area from the given axis of rotation. So this is how we define moment of inertia. Okay. So but this is only valid for a very small area, okay, because if you take any axis of rotation like this, and here if you take an area, so the distance for this small area will be fixed, you can say y, and this area, let's say it is a. But if I take larger portion of area, friends, so in that case we cannot take y, because there will be number of area involved in that large portion of area. Okay, so this definition is only valid for a small area but not larger area. For larger area we have to follow different technique. Okay, so for a small area, which is a, situated at a distance y, the moment of inertia of this particular area from this particular axis of rotation can be written as I equals the area A times y square. Generally small area is taken as dA, so you can write down dA times y square. So this is how we are going to find out the moment of inertia of an area like this. Now we shall see how to use this particular concept to find the moment of inertia of various sections. So friends, now we would like to find out the moment of inertia of a rectangular section. So let's see how we can proceed and find the moment of inertia of a rectangular section, or section which is having rectangular area. Okay, so here if you see, we have got a rectangular section like this, and it is rotating about this axis of rotation xx. So let's see how it looks like. So we have got here a rectangular section over here, and it is rotating about the axis of rotation xx, and the dimension of this rectangular section is given as, the width of the rectangular section is given as b, capital B, and the depth of the rectangular section is given as capital D. Okay, now we would like to find the moment of inertia of this particular section, which is in the form of rectangle about the axis of rotation xx here. Now I cannot use the previous method what I have already explained you, because that was only valid for a small area dA situated at distance, let's say y, from the axis of rotation xx. Okay, so for this particular situation, when you have a small area like this, we can find out the moment of inertia for the small area as dA times square of its distance from the axis of rotation. This is fine, but here I cannot do it because the entire area is spreading from one side of this axis of rotation to another side. Okay, so here if I take y will be coming at the center over here. So this concept will not be valid for this rectangular section. We have to use some other additional method in order to find out the moment of inertia of this particular rectangular section about axis of rotation xx. So let's see how we can proceed about this. So for that sake, what we will do is, we shall be considering a very small area of the rectangular section, or thin strip we are going to consider. So we are going to consider a thin strip having thickness dy at a distance y from the axis of rotation, something like this, friends. So here if you see, there is a thin strip I have taken, and its thickness is dy, and it is situated at a distance small y from this axis of rotation. Now for this particular situation, I can find out moment of inertia of this particular strip, because it is having very small area, that is dA. So the small area dA of this particular strip can be written as, if I write here, so dA means very small area or infinitesimally small area, and that will be its thickness, that is dy, right? The thickness is dy, friends, and its width is b. So I can write down b times dy. So this is the area of this particular strip, and its distance from the axis of rotation is y. So I can find out the moment of inertia of this thin strip. So let's see how we proceed for this. So we can find out the area of the thin strip dA, and that is going to be very simple, b into, that is width of the strip, times its thickness, that is dy. Now since this strip is very thin, so its moment of inertia also is going to be very less, a very small value. Okay, why? Because the area is very small. Okay, so since area is infinitesimally small, its moment of inertia is also going to be infinitesimally small. That will be simply written as area of the strip dA times its distance from the axis of rotation y square. Okay, we have already defined the moment of inertia of small area is given as area times its distance square from the axis of rotation. So we have got the moment of inertia of thin strip. Now I would like to find the moment of inertia of entire rectangular section. So since this rectangular section is continuous, right, so I can integrate the moment of inertia for thin strip starting from this point, that is top of this particular rectangle to the bottom of this rectangle, right, like this, and we can take various thin strips like this, right, like this. We keep on adding from top to bottom. So this is basically called as an integration. Okay, so if you integrate the small moment of inertia about this axis from top here at this particular point, friends, to this particular point, we can find out the moment of inertia of entire rectangular section. So while integrating, we have to be very careful here that when you integrate at this particular point, that is top, the value of y is going to be, depth is how much? Depth is capital D, so it is from here to here is half of depth, that is d by 2. And when you come to this particular point bottom, here your y is going to be, because it is below the axis of rotation, I will take minus, and that is going to be minus d by 2. So this is very important. Okay, so if you want to find out the total moment of inertia of rectangular section, we will integrate from this point to this point. That is, we are going to integrate small moment of inertia. So I'm going to write down that also. So let me write down this. So moment of inertia of rectangular section, that is capital I, is given by integration of small moment of inertia of strip from bottom to top, right? Okay, we can start from less to maximum, so we can go from bottom to top like this. So from minus d by 2 to plus d by 2, and the value is, that is di, small moment of inertia. And this, if you simplify, so here again I am writing minus d by 2, and here I am writing plus d by 2, and di is nothing but dA y square, so I can write down y square times dA. Simple mathematics we are following. Now here the variable is y. Okay, so this dA variable will not work, so we will have to replace this variable dA, but dA is nothing but width of the rectangular section times dy, so I'll write down that also, minus d by 2 to plus d by 2, and here y square will be as it is, and dA is going to be b times dy. B is the width of the rectangular section and dy is the thickness of the thin strip. Okay, like so b is going to be constants, can be taken outside the integration sign. So we will get integration as minus d by 2 to plus d by 2, and this b I have taken outside, I'll write down b outside, friends, here. So inside will be getting y square dy. Now y square dy is nothing but y raised to 3 divided by 3, simple integration. So it is b outside y cube divided by 3 minus d by 2 to plus d by 2. So if you simplify this, friends, this b is constant and this 1 by 3 is also constant, so I can take 3 also outside. So b by 3 will be constant, will be taken outside, and the inside will be getting y cube. So we'll be putting higher limit to it, so we'll be getting d by 2 raised to 3, and then minus, and then lower limit minus d by 2 raised to 3, friends. So let's simplify this also. So moment of inertia of rectangular section would be b by 3 as it is. So this is going to be d cube by 8, and this is going to be minus d cube by 8. This is minus and this is minus, going to be plus. So d cube by 8 plus d cube by 8 will be d cube by 4. And if you further simplify this, you will be getting the moment of inertia of rectangular section would be b d cube by 12. b d cube by 12. So this is the expression for moment of inertia of a rectangular section about an axis passing at the middle of the section like this. Okay, this is also called a centroidal axis. Okay, this way you can easily find out the moment of inertia of a rectangular section. So by following the same procedure, we have got it as moment of inertia of a rectangular section as b d cube by 12. Okay, which is I have mentioned over here. So this way you can find out the moment of inertia of a rectangular section. Now in subsequent lectures, we will try to find out the moment of inertia of other sections such as triangular section, trapezoidal sections, circular sections one by one. Okay, thank you very much.